So when we're doing differential equations or setting up differential equations like this, the thing to be extra aware of is that what you were talking about the differential equation of, meaning when you're talking about how the amount of sugar is changing. So our differential equation should be about the amount of sugar. So over here on the left, the rate of change, I mean the rate of change of the amount of sugar. So since we're saying S is the amount of sugar in pounds, our rate of change is going to be ds dt. For these tank problems specifically, whenever I think about the rate in and the rate out, the rate in is just how much volume is going in times the concentration of that volume. So I'm thinking about volume in times the concentration of that volume. And the same thing for the rate out. The volume out times the concentration of the volume that's going out. The volume in and the volume out are the same. Right? We're putting in 8 gallons per minute, we're taking out 8 gallons per minute. It's the concentration difference. So of course I've run out of room on this first page here. So we're going to have that ds dt. Well, the volume that's going in is we're putting in 8 gallons per minute. And the concentration that's going in is pretty straightforward. It's 1/4 pound per gallon. 1/4 of a pound per gallon. The part that's coming out is always the part that's a little more challenging to think of. We know that we're pulling out 8 gallons per minute. The concentration going out is changing. At the very beginning, before I started putting any sugar, what's the concentration of the tank? That's kind of a dumb question. How much sugar is in the tank? None. So the concentration in the tank is literally 0 pounds per gallon. But then as we start adding sugar, the concentration starts increasing. And so what we're going to see is that in general, the concentration of the well-mixed mixture, that's a great sentence there, well-mixed mixture, is going to be the amount of salt, sugar, we often use salt as an example as well, the amount of sugar in the tank divided by the volume of the tank, which is, I think it was 200 gallons. And notice that the units totally work, right? If we simplify this, we get ds dt equal to 8 times 1/4 is 2, and the gallons cancel to give us pounds per minute. Minus here, it's going to be less nice, but we still get the gallons canceling. We're going to get 8 times S divided by 200, and still pounds per minute. And if I didn't want to write the units, because often, like, it's nice to see how the units are working out the right way, but then when you're actually going to start doing the solving of the differential equation, you don't really want this in there. So I'd probably simplify this down to just ds dt equal to, and that's an S. Sorry, my S's sometimes look like 5s. That's why I often like to put S of t to make sure that we know it's the function S is going to be 2 minus 8S over 200. So that's our setup. Now let's solve it. When he did this in class, did he solve it using separation of variables or first order linear? Or did he solve it even? Yeah. I mean, you can do it either way. Last time we did it using separation of variables, which I feel like is my general go-to, but we could also do it using first order, right? Let's do it the other way, just to kind of change it up. Even though I like separation, I feel like first order might actually be easier in some ways. I don't generally feel like it's easier, but for this type of example, it's not that bad. So let's do it as a first order linear. Or I should say, it's first order linear either way. What I really mean is let's solve it using the integrating factor, which is usually what we mean when we point out that something is first order linear. To do that, we have to rewrite it in the standard way. So first we're going to rewrite as S, sorry, not S, S prime, or ds dt, whichever way you like. Let's write ds dt. And I'm going to bring over the thing that has the essence. It's going to be plus, I should probably reduce that 8 over 200, but I'll do that in a second. 8 over 200 times S equal to positive 2. Or if you prefer, S prime plus 8 over 200 reduces to 4 over 100, which is 2 over 50, which is 1 over 25. That's it. Yeah, 1 over 25. So S prime plus 1 over 25 S equal to 2. And here it's not terrible at all to find the integrating factor. The integrating factor is just going to be mu of t equal to e to the integral of 1 over 25 dt. Please stop me or interject if you have a question, observation, whatever, something.
What we do with mu, like, how does that show up?
Well, so the way we haven't done anything with mu yet, but the way we get mu is we have to write this in the standard form, which is generally we're thinking of it as like y prime plus p of x times y equal to q of x, except here we're using s instead of y and t instead of x. But the idea here is, and then you find your integrating factor by doing e to the integral of p of x. Oh. And that's what we're doing here. We're doing e to the integral of the coefficient of s, which is just going to end up being e to the t over 25. If you integrate a constant, you just get that constant times your variable. All right, and I feel like I've asked this question probably too many times and not the answer, but I feel like we've said that he's just a totally jump to the answer kind of guy. Like you don't have to show all the product rule stuff in the middle and all that kind of jazz. I think that's right. So jumping straight to the end. The solution is always going to look like your function is equal to 1 over your integrating factor times the integral of your q times your integrating factor. There is a process to get there, but if he's not asking you to show it, then you probably don't want to spend the time trying to show it. So in this particular example, that's going to be 1 over e to the t over 25 times the integral of q, which is just 2, times e to the t over 25. And then we actually do have to integrate. Integrating is not terrible though, right? Integrating e to the t over 25 is pretty straightforward. We've got 1 over e to the t over 25 times the integral of 2 e to the t over 25 is 2 e to the t over 25 t divided by 1/25 or multiplied by 25. Let's see. Yeah. So one point of clarity here, right? The reason I multiply by the 25 is because I'm dividing by the coefficient of t here. Right? If you took the derivative of this, the derivative of e to the t over 25 would be e to the t over 25 times 1 over 25, which would cancel out the 25 there. So that's why we're multiplying by 25. Or really, I'm thinking of it as dividing by 1 over 25. I'm dividing by the coefficient of t and x. And I think that's our general solution. I would probably multiply it through and say this is equal to, so we distribute this times this to e to the t over 25 cancels, and you just get 50 becomes 25 plus, we multiply that by that, I get c over e to the t over 25. And that is our general solution. Now we're not done because we were definitely given an initial condition. If we're trying to solve a differential equation and they gave us some initial conditions, that means we should use that information as well. So our particular solution we're going to use the initial condition to solve for our constant. In this, now I haven't said what it was, but if you all know what it was, even if you don't know that you know. I asked you all, how much sugar do we have at the beginning? And you all told me how much? 0. So that means at time equals 0, S is also equal to 0. So if I take my solution, S of t equal to 50 plus C over e to the t over 25, and plug in t equal to 0 and s equal to 0, I'm going to get 0 equal to 50 plus c over e to the 0, which means c is going to equal negative 50. Right? C over e to the 0 is c over 1. And then if I subtract 50 over here, c is negative 50. So my particular solution is going to be S of t equal to 50 minus 50 over e to the t over 25. Or you might see someone write this in a different way. You could write it as 50 times 1 minus 1 over e to the t over 25, or even 50 times 1 minus e to the negative t over 25. Those are all just as good ways of writing our answer. And then, no, it's fine. So yeah, question, Brian.
Would you mind doing it in a separation of variables?
Not at all. I'm glad. I was kind of thinking maybe I should show it the other way to see if it looks different. Because right, so our answer might look slightly different, although I think it'll be the same, but it might just be might work to make them the same. So let's see what this looks like if we do it the other way. And let's just give ourselves a whole fresh piece of paper. So we're gonna. So you really don't need to write any of this down. You're always welcome to not write or write as much as you want. I will post the notes after class. But certainly if you want to not write and pay attention, not that you're not paying attention. Sometimes it's easier to see what's happening if you're not trying to make sure you write everything down. So you're always welcome to write as much or as little as you would like. So let's look back at our differential equation, which we had written as, I had, let's see here. Before I brought everything to one side, I had ds dt equal to 2 minus 8 over 200s. And if I was going to try and solve this using separation of variables, before I did anything, I would definitely reduce this fraction. So I would rewrite it as ds dt equal to 2 minus 1 over 25. Now, you kind of have a choice here, and I usually like to make the choice to make my life a little bit easier. I'm going to have to divide both sides by all of this. I would rather kind of make it a little simpler by getting a common denominator. So you could totally divide, you could totally say, I'm going to do ds over 2 minus 1 over 25s equal to dt. But it's a little bit gross in reading that. It's not impossible. Or you could say, I'm going to rewrite this first as, well, 25 times 2 is 50. So this is really 50 over 25 minus s over 25, which is really 50 minus s over 25, or 1 over 25 times 50 minus s. So I can think about writing ds dt equal to 1 over 25 times 50 minus s and separating the variables now. Dividing both sides by 50 minus s. And multiplying with an s. I just never use the letter s. It always looks like a 5. And then 1/25 dt. That's what I would probably prefer to do. Again, either way is fine. It's just going to be a little bit less work to integrate ds over 50 minus s versus ds over 2 minus 1/25 s. Okay, let's do it. So integrating both sides, integral of 1 over 50 minus s ds equals the integral of 1 over 25 dt. And if we do this, we get the negative natural log of the absolute value of 50 minus s equal to t over 25 plus c. Yeah, I will point out that since S, the amount of sugar starts off as being 0, then we don't need the opposite values because 50 minus 0 is positive. And the amount of S will only ever get larger and larger and larger. It is never going to actually get to be more than 50. I'll explain that a little bit more later. For now, I'm just going to say we can drop the absolute values. I will explain it, I promise. So here we've got the natural log of 50 minus S. I'm going to multiply both sides by -1 to get negative t over 25. Even though I'm not going to say minus c, I'm going to say plus c. You should think about the fact that we really multiplied that c by -1 to get a new constant, which we're also calling c, because we're lazy. We don't want to write all the things. You could totally write more. You could write like C1, C2 if you really want to. I don't think you need to though. Solving for S, we're going to exponentiate both sides and get 50 minus S equal to e to the negative t over 25 plus C2, which we end up rewriting typically as e to the negative t over 25 times e to the C2, and then really we write it as e to the negative t over 25 times a new constant, let's call it C3. That's a C, not an E. And finally, solving for S, we get S equal to 50 minus C3 e to the negative t over 25. And then if we use our initial condition, we set t equal to 0 and S equal to 0, we end up getting 0 equal to 50 minus C3 times e to the 0, which gives us that C3 equals 50. And our solution is the same. Our solution is going to be that S of t equals 50 minus 50 e to the negative t over 25. Which is exactly the solution back the other way. Which is nice to see, right? It's good to see that no matter if you do it this way or the other way, you're going to get the right answer. Maybe your answer might look slightly different than someone else's because you wrote things a little bit differently, but generally, as long as the work is correct, you will get the same answer. Which way seemed better? I kind of feel like the other way was better. I feel like doing it this way, there's a lot more solving, right? This integral is a bit of work, and then there's a lot of solving for S here. Whereas we look back to the other way we did it, where'd you go here? Right? We had to find the integrating factor, which wasn't too terrible, and then we just threw it all into our solution. And this integral, I think, is way easier, or at least not harder than the other integral we did. And the solving certainly, it's already, solved for you. So I think if you have the option, even though this is definitely a change from what I might have said in the past, if your P here is pretty easy, right? Where'd the P go? If your P of X is something like a constant, it's maybe better to use the integrating factor. You have a question, Lexi? That's a good. So most of the time you won't have a choice. Most of the time you'll either have to use first order linear or have to use the other thing, so separation of variables. The only time when it becomes an option really is if you're looking at first order linear, if it happens to be the case that like this function here, basically if P of X and Q of X have kind of like the same quality, meaning they're both like something times e to the x, or they're both something times x to the same power. Let me show you what I mean by this, just because I do think it's worth addressing real quick. So what I mean is, for example, if I have this differential equation, dy dx plus 50x squared y equal to, I don't know, 2x squared. It's certainly set up like someone is wanting you to do it as a first order linear differential equation. You totally could. But since our P of X and our Q of X happen to have the same function of X essentially up to a constant multiple, what you can also do is you can bring everything to the other side except for dy dx. So I get 2x squared minus 50x squared y. And since the power of x or the type of function of x in each of these pieces is essentially the same, you can factor it out. It wouldn't work if this was x cubed and that was x cubed. Sorry, if that was x squared and that was x cubed. If they were different powers, or that was e to the x and that was the natural log of x, or things that just where you couldn't factor out. But if they're kind of pretty much the same up to a constant, you can do this and then say, oh, dy dx equals x squared. Let's even pull out the 2 times 1 minus 25y. Then you can separate. Say 1 over 1 minus 25y dy equals 2x squared dx. And you can integrate. So usually you won't have this choice, but sometimes you will. And if you do, I don't have a good answer as to what is always the better method. There might not be an answer to that question. It might be sometimes first order is really great. Sometimes separating the variables is really great. It just kind of depends on what you're left with. Here, this doesn't seem too bad, but again, when you integrate this, you're going to get a natural log. Then solving the natural log isn't hard, but it's not just a straight shot. Whereas here, finding the integrating factor is pretty easy. E to the integral of 50x squared, which is just going to be e to the 50x cubed over 3. And then the solution, you do get to, I always say, integrating factor is kind of nice. You get to jump straight to the solution. So solution is going to be y as a function of x is equal to 1 over my integrating factor. Oh, interesting. We'll see. Yeah, okay, it's not so bad. Times the integral of q of x times mu of x, so 2x squared times the integral of, 2x squared times e to the 50 x cubed over 3 dx. Here, you would have to do a u sub to solve this. So you'd have to let u equal, I would probably let u equal the entire thing there. 50x cubed over 3. My du would be the derivative, which is going to be 50x squared dx. I would divide both sides by 25. You get a 2x squared dx because I have a 2x squared dx. So that integral would end up becoming, instead of 2x squared dx, I'd have a 1/25 du and an e to the u. Which is going to be 1/25 u. Let's see, which is 1/25 e to the 50x cubed over 3. And then you have to multiply all that by 1 over. So it's not like, it's not perfect. It's hard probably either way. It just depends on which way. Again, bigger picture, you're usually not going to have a choice. If you do, I really like, there's no good answer, I think, as far as like which way is better. It depends on what you like better. Maybe this seems less terrible to you. Maybe integrating this and solving for y seems less terrible. Sometimes there's no answer to the question, which way is better. All right, back to the tank problem we were doing, just because there was a couple of last things I wanted to say. So let's go over here for a second. Yeah. So, yeah, right. You go back here. After you find the general solution, or sorry, the particular solution is this, then you can ask questions like, how much sugar is there after 50 minutes? How much? Which is not really like that interesting, because all they're asking you to do is plug in 50 for t and solve for s. So s of 50 would be 50 minus 50 over e to the 50 over 25 is 2. And they're usually picking like a number that's kind of fairly nice to plug in. It's still not great, right? You'd have to use the calculator to get an approximation here. I don't actually know what this is. It's fine. I would leave it like that. You could also ask the kind of question, which is a little more interesting, as to how long until the tank has 25 pounds of sugar. So then instead of plugging in value for time, you're setting the sugar amount equal to a certain value and solving for time. So you would say, okay, well, then I'm going to have 25 equal to 50 minus 50 over e to the t over 25. And then I would probably subtract 50 there, so I get negative 25 equal to negative 50 over e to the t over 25. And I would probably multiply both sides by e to the t over 25 and divide both sides by negative 25 to get e to the t over 25 equal to negative 50 over negative 25, which is just 2. And then take the natural log of both sides, so t over 25 equals the natural log of 2, and then multiply both sides by 25. Which is approximately 0.7 times 25, whatever that is. I should know what that is. 17.5. Anyway, so it takes about 17.5 minutes to get to, it seems like pretty fast. 17.5 minutes to get to 25 gallons. Sorry, pounds. Oh, sure. All right. So last thing I'll say about this example, and I said this last time, I'm gonna say it again. To me, the most interesting question you can ask about this sort of tank problem is, what's the long-term behavior? Meaning, what happens to the amount of salt in the tank as time just goes on and on and on and on? Or in other words, what's the limit as t goes to infinity of 50 minus 50 over e to the t over 25? Well, writing it this way actually is very advantageous here, because we can see that as t gets larger and larger and larger, e to the t over 25 also gets really, really large, and 50 divided by that, excuse me, it's very, very small. That's going to go to 0. So the amount of salt in the tank is getting closer and closer and closer and closer to 50 pounds, which might not seem that interesting until you realize that that means the concentration of salt in the tank, well, the concentration is the amount divided by the volume. The concentration is approaching 50 pounds of salt, sugar, I keep wanting to say salt, divided by, how big was the tank? I know, 200 gallons, which is 50 over 200 reduces down to 1/4, or 1/4 of a pound per gallon. This is exactly the concentration that we started pouring in the first place. And that is generally true. You have some tank, it's got stuff in it, and you start adding a solution that has some concentration and you're draining it at the same rate, the mixture in the tank will eventually get closer and closer and closer to having the same concentration as the stuff you're putting in. It's kind of cool. I think it's a really interesting thing to see that we can show through these differential equations that, oh yeah, that actually happens. I'm sure people have observed that actually happen in real life, where they have where you're making something and you need to keep the amount, like people, I'm sure with beer, like you're trying to bring beer to a certain alcoholic concentration, you might start adding beer that has a specific concentration to try and percent. Not that we can let time go on forever, but certainly you can get pretty close to this concentration without letting time go on too long. Good. That was a lot of talking about that one problem. That's all right. It's good. It's a good problem. Let's go ahead and look at one of these other problems. So there is a problem I saw someone was asking about in the homework from the book. I don't know if it was a wolf problem or something about, I think it was like number 25 from one of the sections about, well, it's something similar to what I'm going to say here. So logistic growth. So let's say we have the following. In many real life situations, a population is limited and cannot grow beyond a certain size for various reasons, right? It might be because there's only so much prey. It might be because of shelter. There's lots and lots of, it might be because they're being hunted. Right? There's lots of reasons why, in this example, wolves are going to have a cap on how many wolves there really can be for things to start. Like if there's too many, essentially, then there's not enough resources. The logistic growth model assumes that the rate of growth of a population is proportional to both the population P and the difference between the limiting amount L and the population. So sometimes this gets written in a couple different ways. One way of writing this is the following, that the rate of change of the population is proportional to the population and the difference between the limiting value and the population. There are other ways of writing this, but this is a pretty standard way. So, for example, imagine this situation that we know that at time equal to 0, the population of wolves is 20. Later on, at time equal to, say 5 years later, the population of wolves has increased to 50. If the limiting value is 200, how many wolves are there going to be? Or I should say, how long until we get to 190 wolves? So here's so I should say a couple things. So this differential equation looks like dp/dt equal to k times p times 200 minus p. It's not fun to solve. I mean, okay, fair enough. What is fun to solve? You might have different opinions than I do. I really enjoy doing a lot of this math. So it's like, oh, yeah, let's do this problem. But this one is kind of gross. I don't think your teacher really expects you to solve it, but he might. I don't actually know what's inside his head because I'm not him. So let's talk briefly, well, in the last 12 minutes of class here, how you would solve this. And then I have a handout to give to all of you that has kind of more about it. So let me write down a few things again. I don't know how much of this I would write down if I was a student, but let's do it. If I want to solve the differential equation dp/dt equal to a constant times p times 200 minus p. Some people use n instead of p, whatever you like. We have to use, well, first let's separate it. It's definitely, so I will point out, it is definitely not a first order linear differential equation. Specifically, it's not linear. If you multiply this out, you get p squared. So it is not linear in the function p. You have p to a higher power than 1. So good to observe, once you know something's not linear, the only other way you can even attempt to solve it in this class is using separation of variables. Those are the only options available. I will mention just as a side. There are lots and lots of other ways of solving differential equations in other classes, but in this class, those are our two methods. So I just don't want you to think that like, oh, it can't be done ever. So I'm going to bring all my p's over to the left. I'm going to divide by p and 200 minus. So I'm going to say 1 over p times 200 minus p is dp is equal to k dt. And then we're going to integrate both sides. And the bummer about integrating the left-hand side is it requires partial fractions. We did learn last quarter, but we didn't spend a whole lot of time on it. So we definitely need partial fractions. Not too terrible. In fact, it's not the most terrible part of this problem. The most terrible part is actually solving for p once you've done the integration. So let's do this relatively quickly here. I'm going to have my fraction 1 over p times 200 minus p. My partial fraction decomposition is going to be a over the first factor plus b over the second factor. We multiply both sides by the common denominator. We're going to multiply both sides by p times 200 minus p. Sorry, it's a little squeezed in there, I know. It says p times 200 minus p, believe it or not. If we multiply this to here, we're going to get just the numerator. We multiply this by that term, the p's cancel, and you get a times 200 minus p. When you multiply it here, 200 minus p's cancel, and you get b times p. And for this problem, it's always the kind of nice partial fraction situation where you can just pick nice values of your variable and solve for a and b. So I'm going to pick p equal to 0 and get 1 equal to a times 200 minus 0 plus b times 0, which is 0. I guess I can write that down. Solving for a, I get 1 over 200 equals a. In a similar way, I set p equal to 200. When I plug in 200 for p, I get 1 equal to a times 200 minus 200 is 0 plus b times 200. Solving for b, I get 1 over 200 as well. So I can rewrite this integral as the integral of 1 over 200 over p plus 1 over 200 over 200 minus p. Or if I was maybe smarter about it, I would factor out the 1. And I would rewrite this as 1 over 200 times the integral of 1 over p plus the integral of 1 over 200 minus p. Again, the caveat here, I don't really know how much of this your teacher actually wants you to have to be able to do. My guess is probably none, but on the off chance that he wants you to have seen this or experienced it, here we are. So then solving this, I guess I could integrate this. I keep on writing the integral k dt, kt plus c, and then integrating the left-hand side, we get 1 over 200 times the integral of 1 over p is the natural log of the absolute value of p. Integral of 1 over 200 minus p is minus the natural log of the absolute value of 200 minus p.
Still, why would you do a minus?
That's an excellent question. So let me ask you a question. If it was a plus here, what's the derivative of, in fact, let me just write it over here. What's the derivative of the natural log of 200 minus p? Well, I know the derivative of the natural log of x is 1 over x. And more generally, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the inside stuff because of the chain rule. So I take the derivative of this, I'm going to get 1 over 200 minus p. And then what do I have to multiply by? What's the derivative of 200 minus p? -1. But the problem is, I want the derivative to be plus 1 over 200 minus p. So the antiderivative has to have a negative sign here to account for that.
You only put negative ln if there's negative on the inside.
Well, let me give you a more general explanation here, because I think I do think this comes up often enough that you should know that in general, we'll come back to you. Don't worry. Come on. If you're integrating something like 1 over x plus 5, you're going to get the natural log of the absolute value of x plus 5. Because the derivative of that's 1 over x plus 5 times 1. And if you're integrating something like 1 over 3x plus 2, you could totally do a u substitution. I don't think you should have to, though. You could say, well, I know it's probably something like the natural log of 3x plus 2. But I'll ask you all to show me an answer on your fingers in a minute here. If I take the derivative of the natural log of 3x plus 2, I get 1 over 3x plus 2, and then what number on your fingers do you want to multiply by? Because of the chain rule. Yeah, that many. When you take the derivative of this, the derivative of the natural log of the absolute value of 3x plus 2 is 1 over 3x plus 2 times the derivative of 3x plus 2, which is 3. I don't have a 3 here. So I don't want to get a 3 here. So what do? I divide by 3 to account for the multiplication by 3 that's eventually going to happen if I were to take the derivative. So I'm going to toss in a 1/3 there and a 1/3 there, and then the 1/3 times 3 cancels out, and I get the derivative of this to be exactly the function I was trying to take the antiderivative of in the first place. So the more general answer, good question, is that you always end up dividing by the coefficient of x in this sort of thing. So if you do like the integral of say 1 over negative 4x plus 2, it's going to be the natural log of the absolute value of negative 4x plus 2 divided by negative 4. Because my derivative would make me multiply by it. Or back to the original question, if I was doing the integral of 1 over 200 minus x or minus p, it's going to be the natural log of the absolute value of 200 minus x, and then divided by negative 1. But dividing by negative 1 happens to be the same as multiplying by negative 1, so we just put it as a multiplication instead of division. So that's the whole story as to why we're doing that. Yeah, so back to this for a second. Yeah, we got enough time probably. Not you. You. Cool. All right. So solving this is now where things get a little bit gross. I know that P of 0 equals 20. I know that P of something else equals 50. P of 5 equals 50, I think. But to solve for P here, it's kind of a problem because unlike in previous ones where you can only have your thing you're solving for one time, it's showing up twice here. So I would do a couple things. I would multiply both sides by 200. Now check this out. I'm multiplying both sides by 200 and get the natural log of the absolute value of P minus the natural log of the absolute value of 200 minus P equals a new constant times T plus a new constant, where that constant is 200 times that constant. Again, if you like, I can throw in some subscripts there just to make sure you see that they're different. And then we're going to combine the left-hand side as the natural log of the absolute value of P over 200 minus P, using the rules of logarithms. And then E both sides, right? It's a right. This is a kind of a lengthy process, which is why I don't really think your professor is going to want you to actually ever have to do this. So E both sides, you get P over 200 minus P in absolute value equal to E to the K to P plus C2. And you can kind of see here, it's just going to kind of go on. I mean, it is definitely solvable. It just is gross. I should point out that since I know that P of 0 is equal to 20 and P of 5 is equal to 50, this whole expression is positive when I start plugging in values, which means I don't need the absolute value here. If I plugged in those things and I got negatives, I would have to change it. But I can see when I plug in 20 here and 20 here, the whole thing's positive. When I plug in 50 here and 50 here, the whole thing's positive. It would only be negative if I happen to have values that were over my limiting amount. Okay, so drop the absolute values, and then people do all kinds of weird stuff. I'm going to say P equals 200 minus P times all this, which is E to the KT times E to the C, which I'm going to call A. And then, right, it's just, like, how much time do I have? Not much time. I have a minute. So then you get P equal to 200 A E to the KT minus A P E to the KT. You bring this over there, you factor out a P. It starts to feel really silly, but eventually you get all that. So solving for P, we finally end up with P as a function of T equals 200 A E to the KT over 1 plus A E to the KT. Wow. And then you plug in your values here to solve for A and K. So plug in T equals 0 and P equals 20 and solve for A. And then plug in T equals 5 and P equals 50. And solve for K. So seeing all this, you might understand why that problem in the book said use a computer, because it's a giant pain in the butt. Now, the better answer to this question is that there's a general kind of always solution that works. So if you have some sort of logistic growth problem, differential equation, and you know what the limiting factor is, and you know some other piece of information, your solution is always going to look a certain way.